All right, so where we left off was with question 7.26. I said we were going to give this one the old college try. If I can find it again. So right here, there we go. All right, so it says to draw all of the expected products, each of the following solvolysis reactions. So they kind of gave away part of the answer. If it's a solvolysis reaction, that means that you're putting the reaction or the substrate, the starting material, in a solvent. And so we're only going to get SN1 and E1 products. It's the only thing we're going to observe here. So we know the first step for this reaction is going to be the loss of leaving group. And so if we lose our leaving group, we're going to end up with this carbocation, this tertiary carbocation, which we know has no reason to undergo any rearrangement. Okay, this is not going to undergo any rearrangement whatsoever. And so let's start with the elimination products first. And when it comes to elimination, there's two types of beta protons. There's these beta protons here, and then there's these type of blue beta protons here. So if we were to abstract the proton in, let's say, black, we start with that one. We're going to end up with something that looks like this. We have the double bond like this, like that. Okay, so that's going to be one product. If we were to abstract the proton in blue, we're going to end up with this alkene, like this. Now, between the one in black and the one in blue, could anybody tell me which one of these is going to be more stable? Would it be the one in black or the one in blue? Exactly, it's the one in blue, right? Because it's tri-substituted. The one in black is only di-substituted. And so that means the one in blue is going to be the major product, right? It's the most stable elimination product that's going to be the major product. And so we've identified that. Now, with the blue product, is there a cis and trans? The answer is no. And we know that because this carbon has two methyl groups attached to it. Those are identical, so cis and trans does not exist. So these are the two E1 products. We have the major product and we have the minor product with respect to the E1. So I'll just put E1 under these. And then for the SN1 product, what's going to happen is our nucleophile, our ethanol, is going to come in and it's going to attack the carbocation. Then we've got a proton transfer. And so to draw the substitution product, it's going to look like this, where we're going to have our ether like that. So there you go. So this is going to be the SN1 product. So there you go. Problem solved. Done. All right, let's try the next one. It's in a similar vein. We've got a tertiary alkyl halide. Oh, sorry, tertiary benzylic. So this one, let's scribble it down here. This is tertiary benzylic. So this is going to be highly reactive. The leaving group would leave, and we would end up with this carbocation, benzylic carbocation, might I add. So there's our aromatic ring. That's ugly. It's going to look something like that. There we go. So we're going to end up with our carbocation. Remember, when you form a carbocation, the carbocation carbon itself is sp2 hybridized, so it's trigonoplanar. So there we go. There's our benzylic carbocation. There is no reason for this to undergo any rearrangements. Yes, it's resonance stabilized, but there's no reason for it to undergo any kind of rearrangement. So when it comes to beta protons, there's two types of beta protons. There's these ones in black on this methyl group, and then there's two down here on this methylene. So if I was to pull off the one in black, then I would end up with this product. I have my aromatic ring, and I would have my double bond over here, and I'd get something like that. If I was to pull off the proton in blue, on the other hand, I would end up with something that looks like this, where here's my methyl group, and my double bond is going to be here, and I'm going to have my methyl group like this. Now, out of those two products, could anybody tell me which one is going to be more stable, the one in black or the one in blue? Yes, absolutely. Yes, the one in blue. Thanks, Hannah. It's because it's more stable. Yes, for sure. Now, with the one in blue, with that one in blue, could I have cis and trans for this guy? For the one in blue, could I have cis and trans, or E and Z? Could I have two diastereomers? Yes, absolutely. So this one is cis because the two methyl groups are cis to each other. So I'm going to draw the trans. So the trans is going to look like this. All right, so we'll put the methyl group here. There we go. So this is the cis and this is the trans. Now, between the cis and the trans, could anybody tell me which one would be the more stable between the two of those? Let me go back to them. Would it be the cis or the trans in this specific case would be the more stable? Which one looks less sterically hindered? It's going to be the cis in this case, right? The cis is going to be less sterically hindered because here we have a proton, okay? And we're going to have less steric hindrance with the phenyl and the proton than we would in the trans where we have a phenyl and a methyl group next to each other. So the cis compound is not only cis, but it's also an E compound. And the trans compound is trans, but it's also a Z compound. So it's a Z compound as well. And so we have identified the major product of the reaction. It's going to be the cis compound or the E compound, and these are all of the E1 products, just like that. Now, when it comes to the SN1 products, again, we have our methanol, which is going to act as a nucleophile, and it can attack the the carbocation like that. So let's draw the product, and notice, or you probably noticed that when you drew the products, you end up with a chiral center. Okay, if you don't believe me, I'll prove it to you. Okay, so once you have your nucleophilic attack and your proton transfer, you're going to end up with this compound. Let me try to draw that a little neater, where you have the ether coming out towards you like this, plus you're going to end up with its enantiomer as well. So you end up with a pair of enantiomers here. Let's see here. So we'll put the methoxy group over here. There we go, like that. So these are the SN1 products, and since you form a chiral center, you end up with a pair of enantiomers in this case. And so if you're wondering, do you form a total of 5 products in this case? Yes, you would form 5 products, right? 1, 2, 3, 4, 5 different products. So you've got quite a soup that you end up making there at the end, quite a few different products. And so yeah, but again, you saw how we took a calculated approach to solving the problem. All right, first we assessed the solvent, then we assessed the substrate, then we assessed what the E1 products were, then we figured out what the SN1 products were. We figured out Zaitsev and Hoffman, or maybe more higher substitution versus lower substitution, and then E and Z are cis or trans, right? So section 7.9 kind of deals with this whole idea of how do you figure out what the products are when you end up with something like 3 or 4 or 5 products or more. So it says that by now, it should be clear that there are a number of things that you have to take into account when you're determining what the products are going to be. And you've noticed that in many cases, what do we end up with? We get a mixture of substitution and elimination products. So here we have take a look at this one. If we just kind of assess the situation, we've got a secondary alkyl halide, we've got hydroxide. That's a strong base, so we're going to get elimination, but it's also a strong nucleophile, right? It's both. It's a strong nucleophile, and so we get a mixture of elimination products and substitution products. Now it turns out that when your alkyl halide is secondary, that it's actually elimination that predominates and not substitution. And so if you're trying to make a decision about this reaction here, let's take a look and let's see if we can assess this. Here we have a tertiary alkyl halide. We have methoxide. Methoxide is a strong base, and it's also a strong nucleophile, right? We used methoxide as a strong nucleophile. However, is it going to act as a nucleophile in this case? No, it's impossible, because it can't be a nucleophile on a tertiary substrate, but it sure can be a base, can't it, right? The methoxide ion can pluck off this proton here, form the double bond, and lose the leaving group. So in that case, if you're like, what do you mean? We only get one product here? Yes, absolutely. And so you've got to be able to predict whether you get 1 or 2 or 3 or more products. So here's kind of the Sparks Notes version of it. How do you predict? Well, the first thing I would look at is the reagent. Ask yourself, is it a strong base, a weak base? Is it a strong nucleophile, a weak nucleophile? Then I'd analyze the substrate. I'd say, is it primary, secondary, tertiary? Is it benzylic? Is it allylic? And then I would look for any kind of relevant regiochemistry or stereochemistry that I have to take into account, right? For regiochemistry, do I get, di substituted and mono substituted products? For stereochemistry, do I get a racemic mixture, right? Do I get, enantiomers, that kind of thing. So if you're wondering, how do I sort out for the reagent? How do I sort out strong versus weak nucleophiles and bases? Okay, that is on this table right here. Okay, this table is, I don't make my students or tell my students to memorize it, but it's a good idea, and I've noticed that a lot of students do memorize it. So it breaks down what a strong base weak nucleophile is, what a strong base strong nucleophile is, weak base strong nucleophile, and a weak base weak nucleophile is. So if we review these, and you can see that there's some new things in here. Something that's a strong base but a terrible nucleophile would be something like this compound. So this is called sodium hydride. Sodium hydride. And you might be wondering, well, wouldn't that be Na plus and H minus like that? Why wouldn't that be a good base? Why wouldn't hydride be a good base? It's not a good base. Not a good nucleophile. Why wouldn't it be a good nucleophile? Because it's not polarizable whatsoever. And so sodium hydride, if you're wondering about these two, DBU and DBN, I think I have their pictures somewhere. I know they're in the textbook for sure. But the structure of DBN, for example, DBN is the one I have memorized. It looks like this. So it's two rings that are fused together. So you have a double bond here. And then this one is a 6-membered ring like that. So DBU and DBN, they're just very bulky. They're very big, hindered bases. So amines are bases, but you can see how big this thing is. So it's a terrible nucleophile, but it's a really strong base. So DBU and DBN are just big, bulky bases that are terrible nucleophiles, but they are very good at picking up protons. Then strong base, strong nucleophile. Anytime you have an oxygen with a negative charge, hydroxide, methoxide, ethoxide, these are all strong bases, strong nucleophiles. Now, if you're wondering about why isn't butoxide in here, right? The reason why is it is a strong base, but it is not a strong nucleophile, right? It's too sterically hindered to be a strong nucleophile, so it's a strong base only. So you could even pencil that in here, really. You could say terbutoxide, you could put here base only, okay? Because that does show up a lot, but it's a very strong base, weak nucleophile. So technically, it could be put into this section here, okay? So don't put that alkoxide in with those ones. The next one is a weak base / strong nucleophile. So all your halides, iodide, bromide, chloride, sulfide, your thiolates, hydrosulfide ion. And then you might be puzzled by these ones here because all the rest of them have negative charges, okay, and are the conjugate bases of things that are slightly acidic. But if you're wondering why these are good nucleophiles and weak bases, well, first of all, you can see that they're not strong bases. They don't have negative charges. But why they make good nucleophiles is because sulfur is polarizable. And so that means it's able to distort its electron cloud to be a good nucleophile. And then the last one is water and alcoholic solvents, okay? Methanol, ethanol. Those are terrible bases and terrible nucleophiles, right? They're good for what? They're good for solvolysis reactions. Solvolysis reactions, right? Those are only good for SN1 and E1 reactions. So now that I've lost all that, oh, maybe I didn't. Anyhow, so there you go. So to review, strong base, weak nucleophile would be sodium hydride. These big bulky bases like DBU and DBN. Terbutoxide, Again, don't put it in the strong base, strong nucleophile category because it is a strong base, but it's too sterically hindered to be a good nucleophile. The oxides like methoxide, ethoxide, and hydroxide, those are all strong bases, strong nucleophiles. So SN2 and E2 is going to predominate. If you have a weak base and a weak weak base that's a good nucleophile, that's going to be good for SN1 and E1. And then finally, solvolysis or SN1 and E1 reactions, that's going to be water and alcoholic solvents. So again, good idea to memorize this table. You will not be given this. So no, big bases are, yes, they're weak nucleophiles, right? The reason why, Rubio, is if you think about, even if you have a primary substrate, like let's say you had something like ethyl chloride, if the nucleophile is really, really big and bulky like that, it's kind of hard to tell in just a drawing, but it's difficult for the nucleophile to get in there because it's too bulky because of all of this, okay? It can't get into the carbon atom, right? It can't get in there, but it can pick off, right? If I was to draw a beta proton like this, it can easily pluck off this proton, right, and do an elimination. So it's better at picking off protons on the periphery. Does that make some sense? Big bulky bases make terrible nucleophiles. Yep. All right, so then when it comes down to the substrate, again, I brought this table up last class. I said it's wise to have this table, at least part of it in your brain. Whenever you're dealing with a strong base, strong nucleophile, so again, that's going to be sodium hydride, DBU, DBN, terbutoxide. You can put that in there as well. Just going to fix my letter D here. Okay, those are always going to give you E2 reactions, no questions asked. If you have a strong base, strong nucleophile, so that would be hydroxide, methoxide, or ethoxide. Those are all both good bases and good nucleophiles. So if your substrate is primary, yeah, substitution is going to predominate, but you will get some elimination. And this is the one that students get puzzled on the most, or they have the hardest time remembering, and I don't blame you, is that when you switch from primary to secondary, that's when you start to get more E2 than SN2. Okay, so when it's secondary, yes, it is a judgment call. You do get both, but it's mostly E2 with some SN2. And then when it's tertiary, you're only going to get E2 because you can't get substitution. If you have a weak base, strong nucleophile, so there was too many to list here, but we had chloride, bromide, iodide. What else is in there? Thiolates, the sulfhydryl, anion. We said that H2S, right? Thiols, all of those count. Those are all weak bases. They're crummy at picking up protons, but they're all good nucleophiles, and that's because of their polarizability. And the last one, weak base, weak nucleophile, that's just going to be water and alcohols. The water and alcohols like methanol or ethanol. And so water and alcohols are only going to be good at SN1 and E1. Now going back to this one here, I didn't really go over this, but if you have something that's only good at being a nucleophile, if your substrate is primary or secondary, in that case, you're going to get only substitution. But if it's tertiary, it would have to be SN1 because it can't be an SN2. Okay, so that's kind of how we make our decisions in terms of SN1 and SN2 and E1 and E2 reactions. So after analyzing the substrate, so determining whether it's primary, secondary, or tertiary, you can say which mechanism is going to occur, draw all possible regioisomers, stereoisomers, choose the major and minor products using the guidelines that we did. So in the next few slides, he kind of goes over all these different rules. For SN2, he's got rules. For E2, he's got rules. For SN1, there's a bunch of rules. For E1, there's a bunch of rules. I've taught this class long enough to know that for my students, they usually tune me out when I just go over rule after rule after rule after rule. So instead of doing that, what I think is more pertinent is to actually look at some practical examples, okay? And see if we can figure something out looking at a practical example. So let's say you had this question here. See, there's a stereocenter in the reaction, in the substrate. We have a secondary alkyl halide, so I'll put here it's secondary. Then you have a strong base, strong nucleophile. So if we have a strong base, strong nucleophile, we know that E2 is actually going to predominate. So let's go back here and I'll show it to you, okay? If you go back to this table, we have hydroxide on pencil. We have hydroxide, which is a strong base, strong nucleophile, and we have a secondary alkyl halide. So E2 is going to predominate with some SN2. So if there's going to be E2, we have to determine, how many types of beta protons do we have? So let's go back here. Let's go look at our substrate, and you can see that we have this type of beta proton here, but then we also have a beta proton here, right? So not only are we going to get the substitution, but we're going to get at least 2 elimination products. And it turns out that if you eliminate the blue proton, you would end up with this compound, right? But that's a cis compound, and you're also going to end up with the trans compound. So you're going to end up with stereoisomers in this case. So you end up with at least 3 elimination products in this case. So for drawing the SN2, you just substitute, right? You have your nucleophile. It's going to do your SN2, nucleophilic attack, loss of leaving group, and there you go. Now remember, if you have a stereocenter here, you have inversion of configuration. The R gets switched to an S. But going back to the E2 products, right? I had drawn these 2 products in blue a couple of slides ago. But if we look at those 2, if I circle this one in black, let's say, and I circle this one in red, could anybody tell me which one of those would be the major product? Would it be the one in the black circle or the one in the red circle? We know it's going to be one of them because they're both di-substituted. The last one on the far right is only mono-substituted. You're exactly right, Arubio. This one will be the major product. Why? Because this is a trans product, but you can see it's less sterically hindered. So there you go. So we figured out what the most stable product was. It was the di-substituted alkene, which is trans, right? Then we had the cis. Then we had the other product. And then this is a typo here. So this should actually show the substitution product. Who made these slides anyway? All right, so we would put the methyl group down here and the hydroxyl like that. And that would be the SN2 product. So there you go. So that's the kind of decision that you want to make. All right, so now that we have a lot of information, and I mean a pile of information floating around in our brain, let's see if we can tackle some practice problems here. So I'll walk through these with you. Obviously, I'm not going to do every problem in the book. You're going to have to try it on your own. But let's see if we can do this one. Here we have a secondary, come on you, we have a secondary alkyl halide. We have sodium chloride, but right, we're only interested in the chloride ion. The sodium is a spectator ion. Chloride is a strong nucleophile, but it is a crappy base. It is a weak base. Okay, so could anybody tell me what is going to be the predominant mechanism here? Would it be, I'll just let you, could anybody answer that? If I have a secondary substrate and then I have a reactant or a reagent, sorry, that is a strong nucleophile but a poor base, a weak base. And if you have to, you can go back here. Yes, you're exactly right. Okay, you can go back to this table and say, okay, I've got the, where's my red pen? I've got the chloride ion and I've got a secondary substrate. Hey, what do you know? The only thing that's going to happen is SN2. Okay, not too bad. So let's go back here. So we know that the mechanism of this reaction is going to be SN2. Now, there's one other part that I have to take into account, which is what? Is I have a stereocenter here. So that means if I'm doing an SN2, right, if I draw my nucleophilic attack and my loss of leaving group, I'm going to get inversion of configuration. So 1, 2, something like that. And now my product, the chlorine, is going to be going in the back like that. So this is the only product we're going to get in this case, an SN2. All right, let's try the next one. Rubio, I'm not picking on you. See if you can help me through this one, okay? So T-butoxide, right? We think of alkoxides as being good nucleophiles, but T-butoxide is just so darn big. You got these big methyl groups over here, okay? So that's a really hindered base. So is it a good nucleophile? No. Is it a good base? Yes. So we have strong base. I was going to write crappy. We'll put here poor nucleophile. Crappy nucleophile. Poor nucleophile. Okay, and then we have a tertiary alkyl halide. Could anybody tell me what the predominant mechanism will be for this one? It is not a trick question or anything. What's the predominant type of mechanism? You don't have to name the product or anything like that. Yeah, it's an E2. Exactly. Thanks. Perfect. It's tertiary, strong base, poor nucleophile. Don't believe me? Let's go back. Right? This is always murder going back, right? You got strong base, poor nucleophile. So t-butoxide would fit in this category. It's tertiary. It's E. Come on, pen. It's E2 only is what we're going to get. However, how many types of E2 products could you make in this case? While I'm finding the question, could anybody tell me with this substrate, how many different E2 products could you get? Did anybody figure it out? Remember, this is our alpha carbon here. Yes, thanks. Perfect. Thanks for Rubio. Yes. So you have this type of beta proton, and then you also have this type of beta proton. Let's draw both. Ah, come on. There we go. So first I'll draw the one if you abstract the, let's do the blue proton first. So that would give you this compound. Okay. And then you're also going to get this compound. Okay. Let me just erase this. Okay. Now, in this case, right, based off of some of the things that we talked about, you might be tempted to say, well, this one here is tetrasubstituted. It should be the major product. I don't think so. Not in this case. Right? I'd say the compound in black is going to be the major product. Major, since we have a hindered base. Sure, it's a strong base, but it's hindered. So it's going to give you the less substituted alkene. That's going to be the major product in this case. All right. Last one is relative. No, I don't like to use the word straightforward in chemistry class. But DBN, if you remember, it's a strong base. Strong base. Weak nucleophile. It's never going to be a nucleophile ever. Just put here weak nucleophile. Here's your alpha carbon. There's only one kind of beta carbon in the entire thing. And so the only product you would get in this case is just one thing. And it's this compound here. So there you go. So that's going to be the only product. So this is an E2 mechanism. These ones were also E2 mechanisms. And there you have it. So hopefully you guys are picking up on how handy it is to have this knowledge, right? If you have this kind of down pat, you're going to be, it's tough to make a mistake. Well, I wouldn't say it's tough to make a mistake. Anybody can make a mistake. But I'd say it lowers the complexity of the content. All right. There we go. I want to show you some information about other substrates because so far, up to this point in the class, our leaving groups have been basically chloride, iodide, bromide, and chloride have really been the major ones that we've seen, okay? But there are plenty of others. I guess tosylate. So we're going to get into tosylate and mesylate and triflates. And so it says here, there are a wide variety of alternatives to alkyl halides for substitution and elimination. So really all we're talking about here is some new leaving groups. And it turns out that alkyl sulfonates, I'll put here alkyl sulfonates, are all good leaving groups. Okay, they're all good leaving groups. So the first one is what it's called a mesylate. You look at it, you have the oxygen, sulfur with the two double bonds to oxygen. Then you have just a methyl group on it. So sometimes it's called a methane sulfonyl. So methane sulfonyl, methane sulfonyl, depending on where you're from. It's like potato. But the shorthand version is mesylate. The next one, the long form, is to call it toluene sulfonyl. So toluene sulfonyl. And again, you don't have to know that. We use the shorthand, which is tosyl, so a tosylate group. And the last one is trifluoromethane sulfonyl. So I'm not even going to write that down. We use the shorthand, which is triflate. So we abbreviate the mesylate as OMS. So if you have OMS, come on. So if you have some kind of R group and you have an OMS group attached to it, again, the point is this, is that this part here is going to be just like an iodide, bromide, iodine, bromine, or chlorine. It is a good leaving group, right? If you have ROTS, the tosylate is a good leaving group. If you have ROTF, that is a good leaving group. So if you're wondering, why do I have to learn that these are good leaving groups, just like a halide, like an iodide, bromide, or chloride? The reason why is because sometimes we want to take an alcohol and convert it into a good leaving group. So, for example, let's say you have an alcohol, right? An alcohol, right? A hydroxyl group is a poor leaving group, right? It's the conjugate base of water, which is not a strong acid. However, you can do a reaction where you can convert it to a tosylate. Now you've taken a poor leaving group and you've made it a good leaving group, okay? And I'm going to show you how to take a hydroxyl and convert it into a tosylate. So if you're wondering, why do these make such good leaving groups? Well, what did I say? I said that a good leaving group is the conjugate base of a strong acid, or you could think about it as a weak base. Well, the conjugate bases are weak bases. Why? Because the negative charge is resonance stabilized, therefore it is delocalized. But if you want to just look at pKa values, if you like that way, take a look at these. You get methane sulfonic acid, right? That's the acid that produces the mesylate. You see its pKa is less than 0. Therefore, it's a strong acid. Therefore, the mesylate is a good leaving group. If we look at toluene sulfonic acid, sometimes we call this tosic acid. Tosic acid. Its pKa is almost -3. And then look at this one. Then you get trifluoromethane sulfonic acid. Whoa. Sometimes we call this triflic acid. So triflic acid, and you don't need to know all these common names, but that's got a pK of -14. When was the last time you saw an acid with a pK of -14 in this class? Never. So you can see that the triflate is an excellent leaving group, right? It's got such a low pKa. So that's why we learn these. And if you're wondering, oh man, I should use a triflate for everything because it's the best one. You might be tempted to think that, but the one that we're actually going to use the most is going to be the tosylate. Okay, we use the tosylate the most, so ROTS. The reason why is because tosic acid is a solid at room temperature, whereas these are liquids, right? This is a liquid and that's a liquid. So it's easier to work with solids. So how do you make a sulfonate from an alcohol? It's actually a it's a two reagents that you combine together in a one-step process is what I was trying to say. So you use tosyl chloride, which is this compound here. Instead of memorizing the whole name, you can just memorize TSCl. That will work. And then you also use pyridine. So pyridine is a benzene with a nitrogen stuck in the ring, and that's used as a base to pick up the proton. So you can imagine the mechanism of the first step is just nucleophilic attack, loss of leaving group, you end up with an oxonium. The pyridine, which is a base, picks up the proton, and you end up with your tosylate. So you take something again, an alcohol, which is a terrible leaving group, and then once you react it with tosyl chloride and pyridine, so these are the acronyms, TSCl and PY, which is for pyridine, okay? You convert a crummy leaving group into an excellent leaving group. So where was I? All right, crummy, excellent. Okay, crummy leaving group into a, what does it say? Not a good leaving group to a good leaving group, exclamation point. Okay, so that's a real feather in your cap as an organic chemist, is being able to convert an alcohol into a good leaving group. So in terms of the reactivity, it's going to be the exact same as an alkyl halide. So let's say you have a primary tosylate, you treat it with a strong base, strong nucleophile. It means the the SN2 is going to predominate, but you're also going to get some elimination. If you have a secondary tosylate, again, treat it just like a secondary alkyl halide. If you treat it with a strong base, strong nucleophile, the elimination is going to predominate, but you're going to get some substitution, right? You treat them the same way. Look, treat them the same way as you would an alkyl halide. Okay? And in chemistry 3111, so I know all of you are sitting around with bated breath waiting to take organic chemistry too. But in that class, we do a whole chapter. It's chapter 12 in our textbook, which just deals with alcohols. And so we're going to see plenty of examples where we take an alcohol like this. Okay, this is called butanol, and we're going to treat it with tazol chloride and pyridine in order to convert it into a good leaving group. So use it all the time. All right, let's see if we can do some more predictions here of major and minor products. Again, here we have two tazolates. We treat them the same way you would any alkyl halide. So we have a tazolate that is secondary. We have sodium ethoxide. Ethoxide is a strong base / nucleophile. It's good at both. But if it's secondary, that means the E2 is going to predominate. So we're going to get E2 and we're going to get some SN2. There's no stereocenter here to worry about. And there's only one type of beta proton. And so our E2 product is going to look like this. This will be the product of our elimination. And our substitution product is going to look like this, where we just did the SN2. So again, this will be the SN2, and this one here would be the E2, and that's it. Now, in terms of the major product, remember the elimination pathway is going to predominate, and so the E2 product would be the major product, and the SN2 would be the minor product. All right, let's try the next one. We have a secondary tazolate. We have an hydroxide, which is also a strong base / strong nucleophile. And so if it's secondary, just like the first one, the elimination is going to predominate, and we're also going to get some substitution. I'm going to draw the substitution product first because that one's pretty straightforward. We're just going to have an inversion of configuration, and we're going to have our hydroxyl here. And so that is our SN2 product. But in terms of the E2 products, we've got a beta proton here, and we have beta protons here. If I pull off the proton in red, I'm going to end up with this compound. But if I pull off the proton in blue, I'm going to end up with this compound. Now, I'm missing a compound here. Could anybody tell me what compound I'm missing? I'm missing one compound that I haven't drawn that is a product of this reaction. Does anybody know what product is missing? So it's going to be the stereoisomer of the blue compound. So the compound in blue is a trans compound, but I could also draw the cis form like this, or I could draw it like this too. Either one is fine. Yeah, so this is going to be the trans compound, and this one is going to be the cis compound. So the two compounds in blue, those are both di-substituted, but the one that's going to be the major product is going to be the trans because it is less sterically hindered. So this will be the major product of the reaction. It's going to be the trans alkene. And then I have the other alkenes. These are all of these are E2 products, but the one in the blue, it's not good to be a left-handed all the time. Okay, there's a real disadvantage to being left-handed in this world. Anyhow, where the heck was I? Where the heck was I? Let's redraw these products. So we had the SN2 product here. And for this one, first we have the SN2 product, which is this compound. Then we have E1 products. We have this product. Then for E2 products, we also have the trans, and we also have the cis. Okay, and this one is going to be the major product, like that. Okay,